In the last episode, light refused to remain only a wave. It spread like a wave, but interacted like a particle. And then came an even stranger question. If light can behave like matter, could matter behave like light? Physics had already been shaken. Light was no longer a simple wave. It had particle-like energy packets, photons. But matter still seemed safe. A stone was a particle-like object. A ball had a path. An electron was imagined as a tiny, localized entity. Then Louis de Broglie proposed one of the boldest symmetry ideas in physics. If waves can behave like particles, maybe particles can behave like waves. De Broglie suggested that every particle has a wave-like nature, not only light, matter itself. This sounded absurd. How can a stone be a wave? How can an electron have a wavelength? But quantum mechanics was no longer protecting classical intuition. De Broglie connected matter waves to one simple formula. Lambda equals Planck's constant divided by momentum. Lambda means wavelength, the distance from one wave crest to the next. It tells us the scale of the wave. H is Planck's constant, the same fundamental constant that appeared in Planck's formula. It links quantum behavior to a fixed scale in nature. P means momentum. Momentum is the quantity of motion. In classical physics, momentum is mass multiplied by velocity. M is mass. V is velocity. So momentum increases when an object is heavier, or when it moves faster. Now the formula becomes intuitive. The larger the momentum, the smaller the wavelength. A fast or massive object has an extremely tiny wavelength. So why don't humans, stones, and cars look like waves? Because their momentum is enormous. Their wavelength becomes unimaginably small, too small to observe in ordinary life. But electrons are different. They have extremely small mass, so their wavelength can become physically relevant. At microscopic scales, matter wave behavior appears. Then experiments began to reveal the impossible. Electrons could produce interference, not like tiny bullets, like waves. Interference happens when waves overlap. In some places, they reinforce each other. In other places, they cancel each other. This creates a pattern. Bright, dark, bright, dark. That pattern is the signature of wave behavior. But electrons created similar patterns. This was not supposed to happen. Electrons were supposed to be particles. And yet, when an electron reached the detector, it appeared as a localized point, a particle-like event. Before detection, it behaved as if it had wave-like structure. At detection, it appeared as a particle. This was no longer ordinary matter. Then came the most disturbing part. Even when electrons were sent one at a time, an interference pattern still appeared, as if each electron interfered with itself. Classical physics expected a particle to follow a definite path, but quantum matter resisted that picture. The exact trajectory began to lose meaning. Quantum mechanics began replacing paths with probabilities, not because of ignorance alone, but because reality itself no longer behaved like a classical object. And something even deeper was approaching. When physicists tried to observe which path the electron took, the behavior changed. This would become one of the central mysteries of quantum mechanics. The old picture treated matter as static object. Quantum mechanics began showing matter as dynamic structure, not simply what it is, but how it can update, interact, and appear. De Broglie changed the meaning of matter. A particle was no longer only a particle. It carried a wave-like structure, and with that, the Newtonian object began to dissolve. Light had already become both wave and particle. Now matter itself had become wave-like. Classical reality was collapsing from both sides. In the next episode, we enter the experiment at the heart of quantum mechanics, the double-slit experiment, where a single particle seems to pass through two possibilities, and reality changes when we try to look.